Hi everybody, welcome back to the Feynman technique. Today we're going to be taking a look at this integral. I believe this came from the channel Owl3. I will link to his video in the description. He uses a different method to solve this. I don't believe he employs any sort of Feynman integration. I will be employing Feynman integration, and I'm also going to be employing the formula that I derived in my last video. I will also link to that video in the description. But let's just get started. So our first step here is we're going to use integration by parts. And that's the standard integration by parts formula right there. And we're going to let our u equal this natural log x part right here, implying that our du is 1 over x dx, and our dv is going to be the rest of it. It's 1 over 1 minus x. That implies that v is negative natural log 1 minus x. Next, we apply that substitution. So we see that our original integral is going to be our u times v evaluated at the bounds minus v du. So our v is this part right here, and our du is this 1 over x. So we get natural log 1 minus x over x, and then the negative and the negative cancel out. Okay, so next we have to take care of that. We have to take care of this thing right here. Well, that's going to equal, plugging in 1/2 is no problem. That's just going to give you negative natural log squared 2. That's easy enough to figure out. But this part right here might be a little bit more difficult. You can use L'Hopital's rule on that and take the limit as x goes to 1, and you will find that that limit goes to 0. So, um, finally, we have our I is just equal to this negative natural log squared 2 minus 0, of course, and then plus the remaining integral. So I is now equal to this, and we're going to rearrange this because we're not actually going to be using the fact that I is equal to this. We're going to be using the fact that this integral is actually equal to I plus natural log squared of 2. Um, and you'll see why I rearranged that in a minute. Now we're going to be using the formula that I derived in my last video. That is any integral from a to b of any function of x integrated with respect to x can be rewritten this way. And that's useful because having our bounds of integration be 0 to 1 is nice. Because there's a lot of known integrals with the bounds of integration 0 to 1. So applying that to our original expression for I, don't forget our original expression for I was this. So we're going to apply that substitution to our original expression for I. And if you plug in everything, you'll see that this integral using this formula will transform into this. So now we have I is simply equal to this integral right here. I just switched the dummy variable from u back to x. And this one is going to lend itself nicely to differentiation under the integral sign, which we're going to do now. We're going to call f of t the integral from 0 to 1 of the natural log of 1 minus tx over x. And from that, we can see that our f at 1 is just going to be this integral. That is a known integral that I've solved on this channel before, or a variation of it anyway. And that's easy enough to show that it equals negative pi squared over 6. I'll also include a link to show that because that's not something you can get with standard integration techniques, but this video would be too long if I showed every step of how to do that. So we're just going to take it for granted. That integral right there converges to negative pi squared over 6. And you'll see that if we take f at 1/2, we end up with this, which is exactly negative I. So f of 1 is negative pi squared over 6, and f at 1/2 is negative I. Now, we're going to take f prime of t using the Leibniz rule for differentiation under the integral sign, which says we can take the derivative of this expression directly with respect to t by simply leaving the bounds of integration alone and taking the derivative with respect to t inside the integral sign. So we'll have f prime of t is equal to, this is what you get if you take the derivative with respect to t of this, and you'll have a negative sign there. And then if you evaluate that integral, which is easy enough, you'll get natural log 1 minus t over t. All right, and now we're going to use the fundamental theorem of calculus. I believe it's part 2. Basically, if we're going to integrate f prime of t dt from 1 to 1 half. And of course, that's going to be equal to f of our upper bound, 1 half, minus f at our lower bound, which is 1. But it's also going to be the integral from 1 to 1 half of this, which we know from earlier is equal to I plus natural log 2. Remember from earlier when we showed this. And that is exactly the integral we have right there. So that is equal to I plus natural log squared 2. But it's also equal to f at 1 half, which we said is negative I, minus f of 1. F of 1 was, of course, pi squared over 6. So we're left with I plus natural log squared 2 is equal to negative I plus pi squared over 6. And we're pretty much done now. So if I plus natural log squared 2 is equal to I, or is equal to negative I plus pi squared over 6, we can rearrange that and do some algebra and see that I turns out to be pi squared over 12 minus natural log squared 2 over 2. And that is it. So the integral from 1 to 1 half of natural log x over 1 minus x dx is pi squared over 12 minus natural log squared of 2 divided by 2. All right, guys, I hope you enjoyed that, and we'll see you next time.